So, here's the plan. I'm going to combine what would have been the lectures for week 5 and 6 because there's a lot of overlap and it's difficult to separate them apart. So, go ahead and look at this week and next week. Go back over it and do the labs, and we'll talk about it in class. I was thinking about this the other day. We're joking in class about the International Union of Geospatial Wizardry, and I'm looking at my logo here and realizing I spelled international wrong. But I was thinking about something like this, which I thought was kind of funny. And, anyway, so I wanted to share that with you. So it was something I made in my free time one day, just tinkering around. So what are the elements of image interpretation? Well, lots of things, but the first one we look at is something as simple as shape. Many natural and human-made things have a unique shape, things that we don't typically see a lot in nature, or not at the scale, or made out of the materials that we see them made out of. And so we use that as a means of identifying things. And how do we describe it? We talk about how linear or curvy or round things are, as well as other shapes. Here are some examples. When you're looking down from above, an airplane doesn't look like much of anything other than an airplane. All other features are more geometric, like the Pentagon. You can also see how some road designs look quite dramatically different, as well as trees and flowers and vegetation and how they look different. Another thing we look at is shadow. It can be a problem in remote sensing. It obscures objects. However, the good thing is it can help you. Daggone it. I was trying not to yawn this week. It really has the ability to help you figure out what things are, because it can give you some idea of how tall things are, particularly relative to other things. So here we have some examples, and just looking down, you might not notice that thing there in the bottom sort of center of the image, in the top left image, is a water tower, until you notice the size and the shape of the shadow. Now on the pyramids, it kind of obscures a little bit of the look of the pyramid, but that's about it. Same way with the shadows from the highway and the road signs. Another thing we look at is the tone and the color. Any band of color that we look at in a raster image can be displayed in shades of black and white. In other words, it's something gray, somewhere between those. Sometimes they call these the tones. You can see about 40 to 50 of these, and they're related to the amount of light reflected to a specific wavelength or band. And depending on which ones you're looking at, things may look dramatic or very dramatic. Texture is another thing that we can use. Certain features exhibit similar tones, often exhibit different textures. And what does that mean? Well, things that appear to be the same color and the same frequencies and the same wavelengths will have a very different look. Some will be smooth, some will be not so smooth, and others will be really, really rough. And so by looking at this, you can get some idea of how things could be different. So here, for example, we have some vegetation, and you can see that the vegetation in the top and the middle is different color. But when you look at the vegetation, now I'm looking at the top left image, along that bottom side, a lot of differences there. The image directly below that, you can see there are two distinctly different types of plants that are showing up in that image. Moving over to the right, in the top, you can see that you have very distinct changes in the look of the vegetation. Similarly with the other images, you can see that there's changes. Another thing we look for is patterns, because sometimes patterns are actually patterns. And so the random and systematic nature of man-made stuff helps us to identify things. You can look here and see that these are houses following roads, airplanes, or doing it again, sorry. Looking at how a river delta might look. They're unique patterns. As soon as you see them, you can get some idea of what they are. What are some of the elements of image interpretation? Other ones, height and depth. As we discussed a couple slides back, shadows can be helpful in that. You can use that to interpret things and draw a lot of information from it. So here we've got this nice, very busy image, and looking at it, you can see the shadow of some of the things, and then you see this wonderfully tall smokestack. And look at the length of the shadow on that compared to the length of the shadows on some of these other structures. And you can see that that is significantly taller than anything else in the image. So when we look at this stuff, images, we also think about association. This is very important when we try to interpret what objects are. Association refers to the fact that certain features and activities are almost always related to the presence of certain other features and activities. So when we see certain things that could be thought of as something else, we know they're not if we can link them together with other things that we can identify. We go, oh yeah, when I see A, B, and C, I think this. It's like the old adage, when you hear hoofbeats, think horses, not zebras. Well, that's true. But if you hear hoofbeats and you see stripes, you think zebras. So we've got a couple of images here. As far as association, when you look at the industrial layout on the far left in the cooling tower, you think power plant. The one in the middle is a sawmill. How do you know that? Well, you got stacks and stacks of lumber along the left and trees in the middle. And at the other side, you've got a lot of waterways coming in and out and some rather large pools. And I'm not sure what that is, but with some investigation, you could probably get some clues and eventually come to some idea of what you think it is. My guess is it's probably some petroleum distillation facility. So all that's nice and good, but that's more of the more basic form of remote sensing. Sort of, you can kind of think of remote sensing like Neapolitan ice cream, where you've got chocolate, vanilla, and strawberry. You've really, at its most basic core, got like 3 groups of things you can do. You can look for things in pictures, manually, individually identify stuff in images and say, oh yeah, look, that's a car. Or you can utilize the spectral information that's contained within the various wavelengths of electromagnetic energy and to identify signatures of what things are, and then match that up across the image and classify everything out. And there's different variations of how you can do this, but it's still the same basic construct of identifying things based on spectral signatures. And lastly, you can literally measure the shape of things using things like LiDAR and stuff like that. So we can see patterns really good. We can also look at things like spatial things, size, shape, context, spectral things, relative brightness and color. We can do the remote sensing thing, which is usually purely spectral. So let's take a look at some of these. We're going to, from the context of remote sensing, look at supervised and unsupervised classification. But before we get too far into that, we've got to talk a little bit about the pre-processing. This is the basics of what you need to know, sort of a general, loosely arranged outline. So why do we do it? Well, geometric corrections are important because Images have distortions. If any of you have used cameras very much, you know there's a thing called a barrel distortion. Lenses collect light in sort of a unique way, and much like our projections do, they distort the geometry of objects along the edges. So we need to correct for all that if we want to do measurements of importance. We also need to have our images georeferenced so that we know exactly where things are, and they need to be projected properly so that the measurements that we make are in units that are effective and have meaning and that sort of stuff. The second part is radiometric corrections. Now, this can deal with a lot of things. For example, systematic errors. When we get a little further in the semester, you start looking at things like some of the satellite imagery and downloading it, you'll find that there are some satellite sensors that, well, they began to malfunction some time ago. Now they still collect a lot of useful stuff. Problem is, you get some junk going on that you got to fix. And so there's some systematic errors that have to be dealt with. There's also variations in brightness. And so the other thing we have to look at is these converting these digital values that we collect into real numbers in some sort of reflectance or absorption. All this stuff is the kind of things that has to be done before you can do remote sensing. So if we're looking across multiple days, got to correct for that. When we look at how things are lit up, time of day, hillshade topography, it has to be done. It's not super complicated, but if you don't do it, it's a problem. So we geometrically correct georeferenced images, and we end up with something called orthorectification going on. And we use digital elevation models and images to do this, so that we can make every image as if you're looking straight down at the focal point of the picture, right in the middle of the instantaneous field of view for every pixel in the entire image. As far as image analysis, we can adjust the contrast and the brightness and the transparency and all these other things, compare properties between images and whatnot. All are useful things to help us do the things that we need to do. So let's look specifically at geometrically corrected georeferenced images and orthorectifying. And we're going to loosely sort of also look at spatial enhancements. This is use of filters, high versus low, smoothing things out. So if you've got a sensor that's maybe got a little bit of a glitch, you can smooth out the image and sort of absorb that noise. If you're trying to identify objects, you can use certain types of filters that will enhance the edges of things so that you can detect buildings. Lots of things like focal statistics also help us examine a window, and you can determine the size and what statistics you're interested in to help figure out what's going on or what you need to know. We can also use the float tool, which converts pixels to decimals. We can use the band ratio, where we divide one band by another. We can use map algebra, things like the raster calculator, to calculate various indices. So going full circle, digital image analysis, we start off with image processing, we correct the distortions, we calibrate, we can mosaic, all parts of the pre-processing side of things. We can enhance the image, it helps us increase the information. We can go into image classification, where we look for clusters and spatial patterns, things like supervising. Okay, data fusion and GIS integration, which basically means combining data, sources or times, hyperspectral stuff. This is typically what you'll be working with in remote sensing, especially moving forward from this point in class, where we collect many bands of information. And of course the biophysical stuff, where we remotely sense estimates of boots on the ground measurements. So what kind of pre-processing are we talking about? Noise removal, again, getting rid of things by blurring it or smoothing stuff out, de-stripping. When you have whisk broom scanners going from side to side, sometimes they're not going to line up the way you want, and at places you're going to have to take out some lines, line drops, missing stuff, things that don't quite match, and just random noise. Radiometric corrections come from the sun not always being the same bright. That's the distance from the Earth to the sun changes. That's why we have seasons. Was the image collected in the morning, in the afternoon, in the middle of the night? These things matter. At night, of course, you won't get a lot. You get the energy that's radiated back out. So you got to adjust for all of these in some fashion or another. And then geometric correction, where we have raw images that have geometric distortions. Stuff that's along the edge of our instantaneous field of view, things that are off nadir. The various geometric issues that come along with push broom and side sweep or whisk broom scanners. We can create subsets of data. We can stack layers together and mosaic things. This helps us do stuff like reduce our data volume. We can combine bands or come up with unique combinations, like, for example, false color infrareds. So there's just different tools that we can use to sort of work on some of this stuff. Contrast stretching. This is something that we've discussed a little bit during lab, and what it's about is looking at what your digital numbers on your raster should be. And one simple way of doing that is you look at the minimum and maximum values that you have. Okay? And then you take your digital number and you subtract the minimum, and then you basically divide it by the range, or the maximum by the minimum. And so that takes your information and puts it across the 255 band potential that you have, so that you can extract as much information from it as all. And then, of course, there's other ways you can do it: spectral stretching, histograms, linears. That are just different means of drawing out the data and assigning less information to each individual band and spreading it out more so you can see things. You also can, we've talked about smoothing, the process of convolution, which, if you're familiar with the cubic convolution type of resampling technique, that's what this basically is. It smooths things out. It has sort of a moving window. It blurs images. It softens edges. Each pixel looks at a certain number of surrounding pixels, and from that it pulls in an equation whereby it calculates a new digital number for that raster cell that's not based just on the existing cell, but on the ones that are around it. Edge enhancements, the opposite, frankly. It uses these different frequencies to detect color changes, and the values get added back in. You end up with this new composite that is superior for finding edges. It basically looks at when there's dramatic changes in digital numbers across multiple frequencies, and it does this and then enhances that so that you can clearly identify when you have an edge. Multi-image manipulation, spectral can't talk this morning. Spectral ratioing. Think grades, not points. Okay, and so it's a percentage kind of a thing. And so the idea is that, say you've got band A and you got band B, and from day to day, the values that you see in each of these bands can change wildly. But what you're interested in is the fact of, they're all a product of how much of the energy of the sun gets whatever done to it. And so even if the sun energy goes up or down, the amount of energy in each band will go up and down, but the ratio of one band to the other should remain constant. And so you can use this spectral ratioing to basically do that. And then there's indices like the NDVI, the SAVI, the GNDVI, all acronyms for various types of indices. I think the SAVI is a submerged aquatic vegetation indices. just for example. You can look these up and see what they are if you want to learn more about them. At some point in time, you'll probably want to use these. Basically, what it does is it looks at combinations of bands and not just how does the infrared compare to the near infrared. It may look at things like the green minus the red divided by the green plus the red, or something like that. The point being is that you get unique and new things identified that you wouldn't necessarily see by looking at a single individual band. And because these indices are processed on image by image basis, once you calculate one on an image, the final value that you get in that should be transportable and more comparable to the other images that are not necessarily collected on the same day. So let's look at some of these classification methods. All right. There's an old saying. And by old saying, I mean somebody said it before I started teaching this class, and we'll call that old and go with it. Jim Hammock said this, and this is from Unconventional Definitions of Remote Sensing. And you can check that out if you want us to see more stuff like this. Visit this website. And he says you can fool some of the bands all the time, and you can fool all the bands some of the time, but you can't fool all the bands all the time. That means that if you have hyperspectral imagery, you will figure things out. And how do we figure things out? Okay, let's look at how this kind of works. Remote sensing looks at your pixels and it creates these things called decision boundaries. And they're basically lines in the sand where it says everything on this side has got to be a this and everything on that side has got to be a that. Now in this example, say we're only looking at two bands, band 1 and band 2. And from that we do a classification, whether it's the computer making the classes or us identifying the classes. We identify things that we call the X and things that we call Y's. This could be apples and aardvarks, it doesn't matter, just however you want to visualize it. And each of these things have their own unique spectral signature. Okay. Now, once we're looking at the signatures in bands 1 and 2 for these things, they sort of cluster out a little bit. We said these are the X's and these are the Y's. What the remote sensing software is going to do is fit some sort of a boundary between those two clusters. And it's going to say things that are close to the known X's that we have. To a point, we're still going to call them X's. But at some juncture, they're going to start to be closer to the cluster of Y's. Now, when it reaches that point, the software is going to call it a Y. Now, how do we do this? Two basic approaches: supervised, unsupervised. In supervised classification, the analyst identifies representative training sites for each informational class. In other words, when you look at the surface of an image, every possible group or category or class of thing that exists in that image, you have to identify and collect samples for. These are forest. This is grass. This is bare ground. This is asphalt. This is concrete. This is shingled rooftop. This is graveled rooftop. This is metal rooftop. This is shrubbery. This is pond. This is river. This is lake. This is ocean. Whatever it might be. And once you identify multiple samples that not only represent the heart of the class, okay, but the variability within the class. And so you have a good representation of all of the forest, or all of the grass, not just one spot that this is the grassiest grass I have. No, it's got to be better than that. From that next step, there's algorithms within the software that will generate those decision boundaries. In other words, it'll draw the line between the X's and the Y's, or between your two classes across multiple spectra. And that is how supervised classification works. Now, unsupervised classification is eerily similar, but its order is slightly different. The same kind of algorithms that generate decision boundaries look at the data itself and works through it to insert decision boundaries based on how the data clusters up. You tell it something in the order of the number of classes you'd like. It tries to find them, and then it asks you the important question, what is this? And oftentimes that means you need to go back and add things together. Sometimes you have to go back and tell it you need more classes because things that are obviously different to you are showing up as the same thing. So supervised classification, analyst identifies training areas, algorithm identifies the signatures, classifies all the pixels, generates a map. Unsupervised classification, algorithm clusters the data, finds inherent classes, classifies all the pixels, generates a spectral class map, analyst labels the clusters, could involve grouping, and you end up making an informational class map. Labeling of classes, here's some things we can look at here, what goes into this. This bispectral plot is a sort of good example of how you can sort of imagine that line separating the two different classes of things. You can look at it across the entire spectrum and think of it as terms of the individual wavelengths, and how in this example here we're looking at quartz and dolomite and gypsum and kaolin clays and how they signature across multiple wavelengths, or you can have classification maps. These are all different ways of showing the different things. X and Y's, different minerals on spectral curves, chloropleth type or style of map, identifying different classes of land use or land cover. So what's the difference between spectral classes and informational classes? Well, in a perfect world, there's none. If it's in class A, spectrally, it's going to be informational class 1. Class B is going to be class 2. But in reality, it's more like A, B, and C are all 1. It's more problematic if A is 1, 2, and 3, B is 1, C is 2 and 4. And how could that be? And here's an example. If you look over to the right, you've got concrete. The top image. Oh, okay, that's concrete. That's good enough. Looks an awful lot like old blacktop. And old blacktop and fresh blacktop are just the same thing. But one hasn't lost its color, hasn't picked up dirt and dust and things, and so it's a darker color. That can be a problem. That can lead to more like the one at the bottom of the list, the or instead of the reality or the ideal. So what are some of the unsupervised classification methods? Histogram peak and valley finding, and of course the ISO data moving means technique. So histogram peak and valley finding is really kind of easy. You look at how many pixels have a particular DN value. The idea being if something has a signature, the more of it there is, the more raster cells there should be. And as that value changes into a new class, you'll get a new peak. And if you're going back to that XY dividing line kind of idea of how do we separate one from the other, you would look at the histogram like this, and when you see that valley, you would imagine drawing a line right through that. Everything to one side is one class, everything to the other side is the other class. You're simply creating that decision boundary based on the valleys in the histogram. In this example, you would say you probably have 2 classes. Now, there are some assumptions that you have more pixels than mixed pixels, and that classes are distinctive. In other words, that you can tell the differences between the stuff that's in the first peak and the stuff in the second peak, that they're unique enough. But this is where you get problems. You get lots of these little peaks that are part of a big peak. And how many classes are here? That is a challenge. That is where, for example, say it actually is only 2 classes, you would ideally have made enough training classes to incorporate as many of these sub-peaks and sub-valleys so that it would know that this is all the same thing. And if we're you know, using some of the other techniques, that they would recognize that those are not individual classes, but they're not enough difference, or that they're too similar, or that you would combine them in the end of the process. Either way, getting us back to the same thing. But how do you identify if a peak is significant? Well, that's a challenge. One technique is this ISOData technique. It's an iterative, self-organized data analysis technique. It is more robust. The user specifies things like iterations, like how many times are you going to go through this? What is the minimum amount of change that we have to do? It looks for clusters. You can tell it the maximum number that you want. It's usually going to find less. The starting locations are along a diagonal of the first principal component. And after that, it goes through this process of splitting and merging parameters. And so the minimum number of pixels that it finds, and then it merges. The maximum spread, if the standard deviation gets too big within a data set, it splits it. And it just keeps running through this process to refine these data boundaries. And I don't know that these are the best examples of how to explain this. This is what I have, and so I'm going to try to work with it. So you have these locations of pixels that are in this multispectral space. In this example, we're looking at 2 dimensions defined by 2 different electromagnetic bands. And the way this will work is that you'll identify some cluster centers. It looks at the minimum distance to the means, figures out the total distance and all the other parameters. It uses those classes that it sets, works from that. Like we said, it looks at standard deviations within the class and the means, and tries to decide if it needs to bring more stuff in or if it needs to divide stuff out. And it process a second, a third, maybe more. Supervised classification, how we represent the training classes, is actually super important. You could use the actual distribution. It's not efficient. You need to generalize stuff. You can also use summary statistics to help you. Supervised classification, this is the minimum distance idea. And so here we've got the same sort of scenario, band 1, band 2. We've got different data points that represent classes of stuff that we have identified. We know that this was group A, this is group B, this is group C. Based on the means and the standard deviations and all that kind of stuff relative to parameters, you can develop this sort of ellipsoid shape around it that kind of identifies everything that's inside what we provided information on to some probability. And that works great. Things are inside that circle, or that ovate object, then it means that there's a really good likelihood that it is exactly what we said it was. But what happens with pixel X? Pixel X is not in any of them. How far is pixel X from that perfect mean target score? Well, it's really close to C. It's really far away from A. B's kind of in the middle. But it's also very close to being in the B zone, more so than it is close to being in C. So how do you figure these things out? Scenario like this, a lot easier to do. It's going to be in A, right? Turns out you can create these decision boundaries between those centers like this, and this is what you see. Some of the stuff that you thought, or that clearly was in your A training data, ends up being in your B class. Some of the stuff in B ends up in your C. So just another way you can do it. The parallelepiped draws boxes around things. The Bayesian maximum likelihood is another technique. This uses these equiprobability contours, and I think I kind of like something like this best. for me personally. And this is something called a probability density contour. So this is a 3D look at the same kind of things we're talking about. Two different bands. We've got our classes that we described. Urban, water, sand, corn, hay, forest. It literally looks at the probability of what am I and figures out the highest probability of belonging for each pixel. And so the closer you are to a peak, the more likely that's correct. But you can see this decision boundary for these urban classes. The urban class has a lot of variability because there's a lot of different stuff in it. It's not as pure as perhaps like sand. So as you stay inside that red line, it means you have a higher probability of being urban than you do anything else. As you move past that red boundary, you become closer to the foot of one of those other peaks, which means that while you're not maybe perfectly like sand, you're more probable that you're sand than the probability that you're urban, for example. So post-classification evaluation turns out to be really, really important. It is so because it's not one of these math-driven things. It's the analyst's prerogative and responsibility to then go in and assess how well or unwell these techniques may have done. And so it is subjective. And basically you ask that simple question: does the classification look right? You can look at things like minimum distances and maximum likelihoods and all this different stuff and see how the confidence in the classifications are. You can assess the accuracy in various ways. But ultimately it's about just determining whether your classification did its job. Whether you look at it subjectively, whether we look at it from more of a statistical standpoint, or if we just apply some random statistical tests to confirm it. The thing we have to remember is that classification is iterative. So we have to add, we have to delete, we have to merge, we have to do these things with these various signatures until we come up with the best way we can come up with to individually identify signatures and thus classes of these various fields of interest.